Welcome back to differential equations. In this video, I want to talk about Dirac's delta. The idea here is named after the physicist Paul Dirac, who was responsible for a lot of the work in quantum physics. And in fact, Dirac's equation, which is well beyond the scope of this course, but is probably the more famous thing named after Paul Dirac, is the mathematical formalism that brings special relativity, speed of light ideas into quantum mechanics. Sometimes it's called the relativistic quantum mechanics wave equation. Certainly not something we're going to be looking at this semester, but just some context of who Paul Dirac is and where these ideas come up. Physicists will call this thing the delta function. Engineers will call it the delta function. Mathematicians are hesitant, and so I am obligated to put the word function in quotation marks. And just like with the Heaviside function we've looked at previously, the Dirac delta function is generally not defined just delta of t, but is delta of t minus c. You could do this for any value. But instead of writing out a formula, instead of writing out an equation for the Dirac delta, we have to kind of approach it piecemeal. If t is not equal to c, the Dirac delta of t minus c is equal to 0. That's the first property. The Dirac delta function is equal to 0 almost everywhere. Everywhere except for one point. When t is equal to c, then you'll have the Dirac delta of 0, which is undefined. And the last operational property is that the integral from a to b of delta of t minus c dt is equal to 1 if c is inside the interval from a to b. And this is equal to 0 if c is not in the interval from a to b. If you think that that seems weird, you are not alone. As I said at the beginning here, mathematicians will tell you that this thing is not a function. There is no way to use the rules of functions as we understand them in order to work with Dirac's delta. But if you tell a physicist that, they will look at you like you're crazy and say, but it works. Dirac's delta is vital to several areas of physics, mechanics, quantum mechanics, also surprisingly vital to electrical engineering, signal processing, and several other tools. And it really behaves nicely when you have things that are defined based on integrals. One of the reasons that mathematicians will tell you that this is crazy and you can't do it is by trying to draw the graph of Dirac's delta. Right? So you cannot draw the graph of Dirac's delta. The graph looks very simply like a straight line at 0 with a hole in the middle. That's not what we're looking for. But you can kind of sort of approximate it. So the way that I want you to think about this is I'm going to treat Dirac's delta like a Gaussian normal curve that is just squished down so that the width of this goes to 0, or maybe the limit as the width goes to 0. Does that make any sense at all? No, because this is mathematicians trying to do things that don't make any sense. But it kind of sort of almost works. And if you keep that picture in mind, sometimes it will help a little bit with the initial understanding. The application that I want you to think about with Dirac's delta is one of impulse. We have talked many times about differential equations as modeling springs, and I've held my slinky up. The idea of a differential equation as a spring is something that can generalize very nicely. If you try hard enough, most things in the world are a spring in some way, shape, or form. And we've looked at driving functions on a spring, where I take the hand holding the spring and I start to shake it, and doing so causes the slinky to bounce, trying not to bounce it so hard that it makes a lot of clapping noise. Another common thing that will happen with a spring, the thing we modeled in the first place, was you pull it in somewhere, you let it go, and you let it bounce. A third thing that you might do to a spring is have a spring sitting there with nothing happening, and then all of a sudden somebody smacks it, causing it to start bouncing. Dirac's delta models that nicely. Dirac's delta does a perfect job of modeling the situation where you have a spring sitting around doing nothing, and then all of a sudden, at a certain point in time, somebody smacks the spring, causing it to do something, and then you continue onward and watch it as it slowly starts to oscillate and slow down as friction and air resistance gets in the way. All right, so that's the model I want you to think of. And for some people looking at this picture and saying, oh, we're hitting it all at this one instant and that's all that's happening, can give you the picture you need. In order to work with Dirac's delta, I'm going to generalize and say, well, the reason that the 1 showed up here is because implicitly there is a 1 as a coefficient on anything. And we can generalize that idea and say that the integral from a to b of some function f of t times the delta of t minus c is equal to f of c if c is in that interval from a to b and is equal to 0. I'm getting ahead of myself. I'm trying to talk and write at the same time. I apologize. Whatever you put out here, evaluate that at C, and that gives you what happens if C happens to be in the interval you care about, and if C is not in that interval, you get out 0. In order to get the delta function working in differential equations, the tool we're going to use is the Laplace transform. And conveniently, this definition makes taking the Laplace transform incredibly straightforward. The Laplace transform is the integral from 0 to infinity of e to the minus st times whatever function, in this case delta, of t minus c dt. And so using the property of the delta function, I'm going to get e to the minus s times c. And we have a very straightforward way of finding the value of a Laplace transform. So if we have a differential equation, let's look at a very simple spring, y double prime plus y. Right? That is the spring with spring constant 1, no friction, no damping force happening. And our driving function is going to be 4 times delta of t minus 2 pi. So physically interpreting this system, if we're thinking about the spring, at time 2 pi, somebody comes by and smacks the spring. Prior to somebody smacking the spring, our initial conditions say that the spring is doing nothing at all. So to solve this problem, we're going to take the Laplace transform. The Laplace transform of y double prime plus the Laplace transform of y is equal to 4 times the Laplace transform of delta of t minus 2 pi. Laplace transform of y double prime is s squared times Laplace transform on y minus s times y of 0, which is 0, minus y prime of 0, which is 0. We'll leave the Laplace transform of y alone for the moment. And from what we just were looking at, the Laplace transform of the delta function is going to be e to the minus our constant, in this case 2 pi, times s. All right, rearrange a little bit. Now, we need to find a function whose Laplace transform involves an exponential. Right? Y is the inverse Laplace transform of 4 over s squared plus 1 times e to the minus 2 pi s. Remember from our video on the Heaviside function, the Laplace transform of some function f at t minus c times the Heaviside function at t minus c is equal to the Laplace transform of f of t times e to the minus cs. Well, there's our minus cs. In this case, c is going to be 2 pi. And so we have s squared plus 1. The inverse Laplace transform, going back to table of Laplace transforms, that is the function whose Laplace transform is sine of t. But we don't want sine of t, we want sine of t minus 2 pi times the Heaviside function of t minus 2 pi. Although in this case, that's not really going to make much of a difference because adding or subtracting a full period 2 pi doesn't change the function at all. And the Heaviside function is going to give us 0 if t is less than 2 pi, and sine of t if t is bigger than 2 pi. All right. And that makes sense based on what we were just looking at. If you have a spring that is being acted upon and you try to model its behavior, before you act on the spring, it's sitting there doing nothing. The position is 0. After you hit the spring starts bouncing. Its position will oscillate using something like a sine function. I would like you to take a little bit of time to investigate a new function. F of x is going to be the integral from 0 to x of f of t minus c dt. And we are going to assume that c is a positive number. I implicitly have done that throughout. Oh. I said I wanted to investigate another property of delta, and then I didn't write down the delta. So I'm getting a new function, f of x, which is defined by an integral, the integral from 0 to x of delta of t minus c dt. Remember from your introduction to calculus that the indefinite integral of f of x dx is the same thing as the integral from 0 to x of f of t dt. I guess this was an x naught. We could change the initial point. That's where the constant of integration comes from. So what I'm having you look at here is what is the indefinite integral of the Dirac delta, which I'm still resisting calling a function, even though we've established that it works very nicely as a function and we might as well just use it. I'd like you to take a couple of minutes, think about what this is going to look like. I'll see you in the next video.